Not to that scope.
It's just like exams like every other week.
Really?
Yeah.
It's only once a week, and it's like we can come in for it, but it's supposed to be online.
I guess that's one of the benefits of having taken it on Zoom. It was twice a week, and I didn't have to go in, so, but that was nice. All right, statically indeterminate shafts. All right, statically indeterminate shafts basically work in the exact same way as previously done for any type of statically indeterminate structure. But before we get into how to solve for statically indeterminate shafts, let's just do a quick recap. So we previously learned that the governing equations for torsion for a circular shaft, we will only be dealing with torsion for a circular shaft, are basically governed by the strain, stresses, and those equations are basically a function of the radius of the circular shaft. So just so you have it, or for anyone who missed it last class, all of our equations were developed based on a small angle approximation for rotation. If you guys recall, for shear strains, the angle of rotation we approximate as the approximate the small angle that basically develops due to a shear stress or shear force that's imposed on it, we can approximate as the shear strain, which is just going to equal, in this case, the radius of the shaft multiplied by the angle of twist, all divided by the overall length. From there, we can apply Hooke's law to then determine that the shear stress is equal to the shear modulus multiplied by rho, being the radius of the shaft at any point from the center of the shaft, multiplied by the angle of twist divided by the overall length. We then furthermore emphasize this to determine how to calculate an angle of twist through an applied torque, because in a lot of cases you will be given a known torque and have to determine a required angle of twist to be able to satisfy to design the shaft. And from this, using equilibrium, we found that the torque can basically be estimated as the summation of all of the shear stresses multiplied by their approximate areas. That would be the shear force. So the shear force, if you guys recall, was just equal to VA times tau dA. And then obviously rho would just be the moment arm of that, which then is of course how you get the torque in the first place. And what we end up with is we can take out the shear modulus, the angle of twist, and the length, because those are all dependent of our small area dA. And once you integrate that, we get a term known as the polar moment of inertia, which you guys would see as just Ix plus Iy for any generic shape. But for circular shapes, it basically just equals this equation here. J is equal to pi over 2 times outside radius to the fourth minus inside radius to the fourth if there's an inside radius. If there is not an inside radius, then the A just approximates to 0, and then you just end up with pi over 2 times b to the fourth. All right. From there, we did a few examples showing how to design with such equations and also how to calculate the angle of twist for stepped shafts, which we learned was basically just a very similar principle to when we were dealing with axial elongation and compression. Just in this case, it's just a little harder to keep track of which direction the shafts tend to rotate. All right, that's why I like to personally I like to look at it from like a front face perspective and then just either apply a counterclockwise or clockwise annotation to it. So the trick with these angle of twist problems is just really keeping track of which direction of rotation it's going, because again, the images can be a little hard to kind of really look into. All right, so going into statically indeterminate shafts, guess what? It's the exact same as what we had dealt with for axially loaded shafts. All right, so from this case, we know that the statics for a statically indeterminate shaft has to equal the sum of the torques equals 0. And this would just be the total torque that's applied. At this case, it would just be the torque applied at the interspace of the two rods. And that has to basically equal TA plus TB. All right, and this is assuming that TA and TB are both just acting opposite to the applied torque. All right. Technically, we could say that this is like a positive torque, and then we know that the torques here could be like negative. So then you would just get TA minus negative TA minus TB, and then obviously, yeah, again, it's all just a matter of your sign conventions and what you're assuming. All right. We know that from the material behavior and kinematics that the angle of twist, this is our compatibility equation. The angle of twist for TA times L1 over G1, J1 has to equal the torque at B times L2 over G2, J2. And then once we solve for the overall torques using a combination of the statics and compatibility, what we can end up with is just that the angle of twist at the center point of that rod there would just equal, let's see, L1 times L2 T over G1 J1 L2 plus G2 J2 L1. All right, now this is just assuming, again, like we're not replacing any of the reaction forces. This is just basically solving brute force method and just applying a system of equations for compatibility and statics to just basically solve for that final rotation. Again, we need to make some assumptions such as the rotation at this part of the rod here has to equal the rotation at that same point for that rod. And then you just solve for the torques TA and TB and solve for static equilibrium that way. Does that make sense, what I'm kind of talking about? Basically, the internal torque for that rod would be TA, and the internal torque for that rod would be TB. So when you do the math, you would just find that the total angle of twist here is where you get those equations from. All right. Now, the way that I personally like to solve any of these problems is basically by using superposition. The reason being is because when it comes to superposition, it provides a more generalized solution than just using this stepped shaft, and then you don't have to solve a million different unknowns all at once. Instead, you can kind of just, work it out step by step instead of just brute forcing the equations. All right, so when it comes to the superposition method, so I'll write just superposition here. All right, the first step would obviously be remove one of the redundants, right? So if we label this A, let's call this B, and let's call this C. Well, one of the first things that we can do is just remove reaction C. All right, so that's no longer there. And what we would first want to do is just figure out what the rotation at C would be for our initial system, all right? So phi C would just equal, in this case, the applied torque times L1 over G1 times J1. And then the torque in member BC here would actually just be 0 because it's not restrained, right? So all of the torque that's applied here, ignoring this reaction here, just gets transferred directly through here. So the total torque in rod AB is just the torque total. All right. Now, the second would be then to consider the actual applied torque at C, which would be our unknown that we're solving for, which we can call this TC. That's our reaction torque that we're solving for. All right. So then I'll put apply redundant. And what we get is TC, or the rotation at phi C. I'll put a bar above it to indicate that it's the secondary system. If you guys were dealing with like, from chapter 9, when we were dealing with deflections, we used the quotation marks with the 1 and the 2 or whatever. So you could do that too. All right, I'm just doing this just to be quick. What we would end up with is the total torque would be transferred between member AB and BC. So the torque felt by both rods is, of course, TC. So what we would end up with is TC times L1 over G1, J1, plus TC times L2 over G2, J2. All right. And then from there, we would obviously apply compatibility. So our compatibility equation would just tell us that phi C plus phi bar C has to equal 0, which then tells us that T L1 over G1 J1 is equal to, I'm going to say TC times L1 over G1 J1 plus L2 over G2 J2, and that would obviously be a negative torque. And then lastly, you just solve for TC, and what we should end up with is negative T times L1 over G1 J1 divided by L1 over G1 J1 plus L2 over G2 J2. And then, of course, from there, you can solve for equilibrium using the equilibrium equation that we used previously. Just, of course, in this case, instead of it being TB, it's TC. All right. Does that make sense? So 2 methods to really solving statically indeterminate problems. You guys have seen both methods for axial loads and honestly even for beams, even though for beams it would be an absolute nightmare to try and do it the first method. But yeah. Are there any questions about the statically indeterminate shaft as we kind of went over it just now? No? All right. Now we have composite shafts. All right. Same principles as with axial loading. Just in this time now, my question is, what's the one rule about composites that we need to remember? All right. We did it for concrete beams. We did it for regular composite beams. We did it for composite axial loaded rods. Hopefully you guys should be able to tell me by now what is the compatibility for composites. What?
You have to find N.
What do you mean N?
Like the
Oh
ratio?
yeah, the modular
Is that
ratio.
what you're asking?
I wouldn't say it's necessarily needed. The only time it's really needed is when you have the beams because it just simplifies the problem process, but that's just an additional term just to help clarify things. So, but what was the one rule that was applied to all composites in being able to solve for everything?
Was it the strain?
Yeah,
Share?
the strains are shared. All right. In this case, it's going to be the shear strains due to the angle of twist being shared. So what we have is basically that gamma 1 has to equal gamma 2. And then as you add more and more of those rods along the outside, they just build up. All right. So this is our compatibility. All right. In the case of this rod here, if we recall, the shear strain is equal to C times phi divided by L. All right, so, but we need another expression for it. So I'm going to use this one here. T times the radius divided by GJ. So TR over GJ. Wait, hold on. Let me just make sure I got that right. T rho over GJ. Rho is the radius. Yes. Is equal to TR over GJ. But that's going to be 2, 2, 2, 1, 1, 1, 1. All right. If we recall that the torques and the radius, all of these are their own independent thing. All right. But we know from equilibrium that the torques from the sum of the torques has to equal the total torque, which is just equal to T1 plus T2. All right. Now, one of the things that I don't like about this compatibility problem is the fact that I think I chose an improper way to use the strains. So I want to use a different strain equation. So I'm going to just cross that out really quickly. Even though it is technically true, we want to find something that's going to simplify the problem. All right. So I think we know that the strains are also equal to the angle of twist multiplied by the, okay. Or do I not want to erase it? I don't know. Let's figure it out. Let's look at our terms here. T times R. What is the other equation for angle of twist? I'm like blanking right now. This is the one that I'm thinking of. Rho times phi over L. But then we need that to be a way to express it as terms of torque. Where is it? Where is it? Whatever. All right. Well, basically, we know that because the length for rod 1 and rod 2, they're the same, right? So by assumption, we can also technically say that phi 1 is technically equal to phi 2, right? So we can now kind of express it in a different manner. All right. So in this case, what we end up with then is if phi is equal to TL over G J, then we get T1 L1 over G1 J1 is equal to T2 L2 over G2 J2. All right, but L1 is going to equal L2. So then we could just rewrite T1 in terms of T2 using just G1 J1 over G2 J2. And that basically kind of gets rid of the need to use that because we don't want to have that radius term because that's just going to complicate the problem a lot more than it honestly I think needs to be. All right, so the angle of twist needs to be the same. All right, so then from there we could just plug it back into the equation, and then we would just be able to solve for the total torque T1, which would just be T is equal to T1 times 1 plus G1J1 over G2J2, which means that T1 is just equal to T times G2J2, and then I'm just going to raise it to the negative 1. It's just the inverse of that. All right. And then from there, because we now computed T1, we could figure out the angle of twist by just plugging in T1 L1 over G2 J2, which would just basically equal, let me erase all this just to make room. Why am I erasing it? Insert new slide. So phi would just then, it would just simplify over to T times L over G1J1 plus G2J2. That's what this would simplify into. Make sense? Obviously, it won't look as clean once you do it at first, but like, I mean, everything will look nicer once you simplify things. All right. Now, let me ask this. How does the stress distribution look for a composite shaft? Right. Let's assume that we know what T1 and T2 are, and depending on how it looks, we can actually kind of figure out some shapes. So this would be like the interface 1. Let me try and shade it as best as I can to match the colors that are being used. So that's that hollow core that's in there. Can I say it's kind of like that? Not at all. Not good enough. What do you guys think the stress is going to look like? The stress distribution from the outside, from the inside going out. So if that's the center, how would it look?
I mean, there would be more stress the further you go from the center.
Exactly. So obviously it's going to be 0 no matter what at the center because the radius is 0. All right. Think of that as kind of the neutral axis. All right. And if we work going outwards, let me see if I can't increase the size of this. There are really kind of two possibilities that you can have. The first would be assuming that you're going right to that interface. The first option could be if the outside material is much stiffer, then what you might have is like an immediate jump and then an increase. Right? That's one option because now you're changing interface, so the stresses will just increase accordingly. Or if you have a less stiff material, what you could have then is a drop and then it still increase linearly as it goes outwards. So that's option 2. And this would be option 1. And you would basically be able to figure that out by plugging in the appropriate radius locations because, again, your shear stress equations are dependent on the radial position at the point of interest. So obviously, if you were trying to find the maximum shear stress in the gray rod, you would only use the inside radius of the orange. You would only use basically the radial bounds in which those materials are confined in, right? Not if you were trying to find the maximum shear stress in the rod, you wouldn't just go straight to the outside. All right, you would need to figure that out, and it would be a very problem-specific thing. Does that make sense? All right. I want to, I guess, show you guys. So let's assume some properties really quickly. Let's say, let me pull this up because I want to see. I just want to show you guys with numbers how it could potentially look. Let's see. All right, so let's assume first, I don't know, steel has G1 is equal to, I don't know, 11.2 times 10 to the 3 KSI, and then G2 is more stiff, no, less stiff, being 3.7 times 10 to the 3 KSI. All right, now let's say that the radius of the outside is, I don't know, say it's like 1 inch, and then R2 is about 1/2 inch. So this would give us J1 and J2. This would be pi over 2 times 0.5 to the 4th, and this would just be pi over 2 times 1 to the 4th minus 1/2 to the 4th. Need my calculator. Let's see. Pi over 2 times 1 to the 4th. This would give us 1.473 inches to the 4th for J1. And then 0.0982 inches to the 4th. All right. So from there, we can figure out what the torque in rod T1 would be. T1, we can just plug in chug since we already kind of did it, would be the applied torque, let's say, I don't know, 1,000 kip inches. So, or, yeah, 10 kip inches. So T1 would just be 10 kip inches times the length, let's say length of, I don't know, 8 inches, divided by G1, 11.2 times 10 to the 3. Nope, I just realized I'm going way off. I'm following the wrong equation. Times 1 plus G1 J1 over G2 J2. So G1 is 11.2 times 10 to the 3 times J1, which is 1.473 inches to the 4th, over G2, 3.7 times 10 to the 3 times 0.0982 inches to the 4th. And that's all to the -1. All right, so we plug all that in. What we get I get a torque of approximately T1 equaling 0.22 kip inches, which would mean that T2 is far greater, of being 9.78 kip inches. And then if we wanted to compute the stresses given these torques, we would just use our TR over J equations. So we would have a tau max for item 2, which would just be 9.78 kip inches Wait, but that doesn't seem right. Did I do this wrong? This whole thing is for T2. That's where I'm going wrong. I just realized that because if I'm replacing T1, then T1 is in terms of T2. Does that make sense? Sorry, I'm like going a little fast. But I replaced T1 into that equation there, which is in terms of that T2. So the T1 gets replaced with the T2 times G1J1 over G2J2. That's where I messed up. So technically, this should be T2, that's T1, and that's T2. No, that's still wrong. T2 and T1. I would expect that because we specified that the outer shell of the element is stiffer, so we would expect a lot more torque to go towards the outer element. That's why. So that's just a quick correction. That's T2 and that's T1. All right, so that should be 0.22 kip inches. The radius of J2, we said was 0.5 inches. And then J2 we said was 0.0928. 982 inches to the fourth. All right, so 0.22 times 0.5 divided by 0.0982 gives us a stress of around 1.12 KSI. Now tau min for item 1 would use that 9.78 kip inches. The same radial position is 0.5 inches. And this time you're using a J1 of 1.473. Which gives us a stress of around 3.32 KSI. So we can see that there's actually a jump in the stress at that interface. And that's because the torque of that steel rod, item 1, is larger than the torque in item 2. Not to mention, of course, the radial positions are going to increase also. And then, of course, you could determine the max stress in 1 by now just replacing that 0.5 with the 1-inch radius that we specified. So it's just double, which gives us a maximum stress of around 6.64 KSI. And so if we were to draw that, let's say that this is the radial point, and this is the interface point where all of this is 2, and all of this is 1. Our shear stress distribution would look like this. This would be tau max 2. And then this would be tau max 1, tau min 1. And increasing till it's about double. Does that make sense? So I just wanted to show you guys how that interface would potentially look. Are there any questions at all about this problem that we just kind of worked on? Yeah.
That slope in section 1, is that always gonna be the same, or can like vary with respect to?
To
Like-
what?
Like the change in the actual, like the slope of that line, like how aggressive it'll change.
It can change because technically then the stress, like it would just be the torque, which would be a constant divided by J, which is a constant. And then the only thing that varies is the radius. But the thing is, the torque over J is different from this element and this element. So you have to look at the T over J, and that would give you what the slope of that is.
Okay.
Make sense?
Yeah.
All right. Any other questions about that? No? Cool. All right. You're not going to throw up, are you?
No, it's for my tissues.
It's what? Oh, tissues. Got me worried. I was like, you're not still sick, right? Or your car didn't break down again. All right. So, now we go into the design of transmission shafts. Not my preferred topic, but that's because I, as a civil engineer, am afraid of things that move. All right. But to those of you who are in mechanical engineering, will actually enjoy this. Basically, as you guys know, when you're dealing with torques and angles of twist and all of these things are applicable to a lot of machines that actually move. For example, a car engine, design of a transmission shaft, design of engine pistons, all of that stuff. And so what you need to figure out, obviously, is power output from said torque. All right? So you guys should know that the power is just equal to the torque times the angular rotation. Not angular rotation. Is it angular velocity? I can't remember all the terms, so please excuse my incorrection of dynamics. All right? And basically, you would be able to find what the torque output would be based off of the frequency of the number of rotations, and you would be able to design for that accordingly. Now, based on that, you as a designer would obviously be in charge of selecting material and dimensional properties, and of course the cross-sectional properties needed in order to be able to handle the shear stresses that are imposed on it, right? So, obviously, when we were trying to find a maximum allowable cross-section, and you're given a specific type of power output, then of course you can figure out everything just knowing what the power of a particular engine is. All right, so in this case, the maximum shear stress is what you would design for, and then of course you guys can kind of figure that out from there, just knowing what the polar moment of inertia would be and what the required radii would need to be. All right, so just a quick example. Here we're asked to design a solid steel shaft to transmit 100 horsepower at 1200 RPM if the max shear stress is not to exceed 7500 PSI. And we're going to take G, the shear modulus of steel, is equal to 11.2 times 10 to the 6 PSI. All right. Now, one of the things that I want to ultimately, hold on, let me look at these notes again. Okay, so we know that the shear stress is not to exceed 7,500 PSI, all right? What does that mean? So if we say that the shear stress of steel, do you guys remember what the maximum shear stress of steel is? Anyone know? What about yield strength?
50 KSI
Depends on the steel type.
or 36.
Yeah, exactly. So from that, we can actually find out what the approximate yield strength for shearing is. That's approximately 60% of the, let me use sigma y, not fy. If I start using different variables, that's actually what's used in a lot of practice in industry is F for stress. So if you guys see that ever and think, what is that? That's force, right? No, it's probably stands for stress. It's weird. All right. So the shear yield strength is approximately 60% of the normal tensile yield strength. That comes from certain failure criterion. I'm not going to go too much into detail on that. But ultimately, if we were dealing with, for example, an A36 type of steel, so let's say that for 36 KSI, then the shear strength would obviously be 0.60 times 36, which would give us around 21.6 KSI for the maximum shear stress. All right, which then would basically just tell us that we're dealing with a factor of safety of around 21.6 times 1,000 divided by 7,500. That gives us a factor of safety of around 2.88. So that's just for your own kind of sake of knowledge. If we wanted to deal with something of a lower factor of safety, we would obviously choose a shear strength that's obviously higher. But in this case, we're just going to deal with the 7,500 PSI. All right. So we know that the power of the shaft has to be 100 horsepower, which does anyone know the conversion from horsepower to pound-feet per second? Not a clue. All right. Let me look that up really quickly because it says right here in the notes, but like there's a bunch of conversion factors also in like the textbook, I believe, that would be able to just tell you what it is. So let me see if I can't find that really quick. Or should I just ask Brianna as a joke and just have her panic? And everything. Where is it? I don't think it's in here. Darn. All right, well, I'm going to just... So it looks like 100 horsepower is just the equivalent of 55,000 pound-feet per second. So if you can't find a better conversion factor for that in a textbook or somewhere, oh, it's right here. So if you actually look in your textbooks, the textbook actually tells you that for power, 1 foot-pound per second is equal to 1.356 watts. And then 1 horsepower is equal to 745.7 watts. And so, do the math. So 745.7 divided by 1.356. Yeah. So then that means that 1 foot-pound per second, yeah, is approximately 1 horsepower foot-pound per second. So that's where the conversion factor comes from. That's in Appendix A. All right. In case anyone's wondering. Not that I just pulled that number up out of thin air. So you can actually find that number. All right. Now, it also tells us the RPM, which means that we can actually figure out the frequency at which it's rotating. So the angular rotation, W, we want to convert that to a type of frequency. So that would just be equal to the 1200 revolutions per minute. We want to multiply that by pi radians per revolution. And then we just multiply that by a conversion factor of 1 minute over 60 seconds. And that should give us an angular frequency of around 40 pi 1 over seconds. All right. Now from there, we can calculate the torque. Wrong thing. We can calculate the torque given that T is equal to P over omega. So that's going to be equal to the 55,000 pound-feet per second divided by 40 pi 1 over second. The 1 over seconds obviously cancel, which should give us a torque of around 437.7 pound-feet. You can multiply that by 12 if you want to work in inches, then that's approximately equal to 55,250 pound inches. 52. All right. And then from there, it's just smooth sailing because now we determine the torque that we need to design the shaft for. So we could just use all of our equations that we had been previously dealing with to figure that out, which would just be tau max is equal to TR over J, and that has to be less than tau allow. All right, so from there, the torque of 5,252 pound inches multiplied by a radius r. That's going to be the outside maximum radius. We don't know that. Divided by the polar moment of inertia, which is going to be pi over 2 r to the fourth. Again, we don't know the radius. And that is going to be equal to 7,500 psi. The r's will just cancel, so that becomes r cubed. And what we end up with is r cubed is equal to 7,500 psi over 5,000. No, I'm jumping the gun here. We end up with 5,252 pound inches divided by 7,500 psi multiplied by 2 over pi. Take the cube root of that whole thing. And then R just ends up equaling approximately 0.764 inches. All right. What radius would you use for the shaft then? Is a 3/4 inch radius good? No. What if you wanted to use a factor of safety of 2? Is it still good? Factor of safety of 2. What was the factor of safety that we specified previously?
2.8.
Yeah. So I would say if you wanted to reduce the factor of safety a bit, like for example, if code specified like you need a factor of safety of 2.5, then obviously the specified shear stress that you provided is obviously a little too low. So you could increase that. So you can technically kind of get away with using a 3/4 inch rod. Ultimately, that's going to be an engineering decision that you would make. But in this case, because the problem says to use 7,500 psi, we would obviously need to enforce that. All right. Any questions about that example? Main gist of that problem is just recalling the, I think those equations are provided in dynamics, right? Like, I mean, yeah. So now you can go to Francelon and be like, We learned dynamics and strengths today. All right. Another topic, stress concentrations in circular shafts. Guess what? They function the exact same way as all of the other stress concentration problems that we had previously dealt with. Just in this case now, it's just torque, all right? So the idea of this would be first to look at the table here for the given load and boundary conditions. Of course, these geometries will vary, depending. So there's obviously a bunch of other tables. This is a very common example when the shaft has that little corrugation there. And what you would basically do is just find the radius of the chamfer, divide that by the smaller diameter, and then from there you would pick out the ratio of D, capital D over D, or the big diameter over the small diameter, work tip to tail, and figure out your K factors, and then just apply all of the equations that we had previously been working with already, and just multiply your average torsional shear stress by that factor K. So previously we had dealt with sigma max is equal to K times sigma average, right? Well, in this case, the torsional shear stress that we're dealing with is already a tau max. So that's why don't get confused when you have a tau max for when you have basically two tau maxes. It's because the maximum shear stress within the small shaft here increases gradually due to the stress concentration. So you get the ultimate max stress that's within the rod equaling the stress concentration times whatever the maximum shear stress is in the smaller part of the shaft. And the reason for that is because this table or this analysis ultimately assumes that the torque within capital D and lowercase d are the same. Is this true? Again, it's very problem specific. You would need to perform the analysis to validate that the torque in the larger portion of that rod is in fact larger or not. All right. A good example of this would be if you were looking at the torques in this problem here, right? Like if there was a chamfer here that was resulting in a stress concentration, we kind of neglected it previously. If I were to give you guys a stress concentration problem, I would obviously specify to you guys the geometric constraints at that region there. And so you would just conduct your analysis the exact same way, just considering the K factor at that point. Any questions about stress concentrations at all? All right. So just as a recap for torsion, ultimately the equilibrium is just equal to the sum of all of the shear forces multiplied by their associated moment arm. The sum of the shear forces is then just, the integration just becomes the integral of the area times the moment arm of each individual small area multiplied by the shear stress that's felt at that location multiplied by the area of said element that you're considering. And when we basically do that, we end up with a total torque that's basically applied to the rod. From there, we can actually derive equations for how to calculate the angle of twist based on a given torque or vice versa, knowing that the relationship is entirely bounded between Hooke's law. So it's all just kind of relating back to day one of the class: equilibrium, kinematics, compatibility, and Hooke's law. All right. Now, I've got some supplemental chapters here. These aren't going to be covered on your exam, but they are a little important to kind of go into because, again, they can still apply. For example, plasticity within torsional rods. What happens when our rod starts to undergo some type of yielding. All right. So as we learned, equilibrium is just the sum of the shear stresses times their areas times the moment arm of each area. We can apply kinematics, but as we have already seen from the material properties, once we reach plasticity, guess what? Hooke's law doesn't apply anymore, right? Because the material has yielded, which means if you're assuming like an elastic, perfectly plastic model, then our stress strain curve, if that's tau and this is our strain, then we can't assume Hooke's law. Which means that the angle of twist can't be assumed to be that equation, and all of our assumptions are just basically null and void. How do we deal with this, though? Well, the idea is just to, again, we want to consider how the diagram is ultimately going to look and look at how the stresses would really vary in the cross-section. If we're assuming full yielding of the cross-section, you guys remember when we dealt with beams, how for a beam, once you reach the plasticity or full plastification of the cross-section, then you had the top having to equal the bottom for the forces, and then from there you could determine the plastic neutral axis, right? In this case, it's a little simpler with the plastic neutral axis technically being at the center of rotation. It's just now you're just assuming full yielding of that entire cross-section. Granted, you can also have some partial yielding. So for example, it could increase linear elastically for some small region here, and then it could just plateau at the top. So it all just kind of really varies on what the force is and how much yielding you're really expecting within the problem. But the only complication is basically just at what force does it yield, and then how does the system behave afterwards, and then just performing iterative checks to really validate that. All right. So if we first assume that the material behaves linear elastically, we can actually find out what the yield strength would be. This yield strength would just be derived as basically being the tau y value, and it would just basically equal the applied torque at yielding multiplied by the ratio of C over J. All right, that's given right there. Ty being the torque that's applied. So if you were just gradually increasing the load more and more and more, you can just iteratively figure it out. But of course, once you reach, for example, steel, a yield strength of the 21.6 KSI that we had seen for A36 steel, then of course, now we need to consider the next regions. All right, I'm gonna go actually and swap those. All right. So in the case of the development of the plastic zone, this is when our material begins to start yielding. So once it starts yielding, what we'll notice is as you apply more and more torque, the stress will increase linearly for some small region because, again, for some particularly known radius, our shear stress as a function of radius can still be below the maximum shear stress, right? Like if you were to necessarily do the calculations and apply the math, you would find that if you tried to obey linear elasticity, your shear stress would be way up here, which obviously breaks the case. All right. So you can't exactly do that. So instead, we need to consider the elastic core. And what we would observe is that as the radius approaches 0, the angle of twist approaches infinity, which again makes sense because when we're dealing with yielding, our stress strain curve is ultimately assuming that at that point, the deformations will just blow up as we apply more and more load. All right, so from here, we can actually find out the total torque at full stress. And what we would ultimately find is once you perform the integral and take antiderivatives with respect to both the angle of twist and the radius, you would ultimately find that the total torque in which full stress occurs would equal, I can't exactly grab that, but it would just equal 2/3 times pi times whatever the shear yielding stress is, multiplied by the outside radius cubed minus 1/4 of the yielding radius, where the yielding radius would just be the radius at which yielding starts, all right? So you can kind of see, like, just mathematically how it would kind of work out. Are there any questions about this at all? Does anyone need a little bit further explanation behind what's kind of going on? No? All right. Well, we can also, just using that, we can kind of calculate what an equivalent torque would be in which the elastic region would still occur. So we could find a total torque that would really be applied. And if we still consider the elastic core, we can use the compatibility equations in which you would, of course, need to figure out the stress profile. And knowing all of that, you can figure out the torque at which the full stress field kind of occurs. And yeah. Yeah, so this torque would ultimately be the torque of this elastic region here. Which would just obviously be a function of the angle of twist at which yielding occurs. So the angle of twist for this outside core here, it's not writing, divided by the angle of twist at which is still behaving linear elastically. And then lastly, one of the simplest cases is just when you have full yielding. If this is the case, then you would basically be able to calculate a total plastic torque, and you can kind of relate that to what the yield torque would be. This is very similar to the cases of when we were dealing with kind of the maximum shear stress versus normal shear stress, or better yet, I'll actually say the difference between, do you guys remember for beams, the difference between Z of X and SX? Right, the plastic section modulus and elastic section modulus, you would be able to derive similar terms, but in this case, because obviously you're dealing with a circular shaft with a very simplified geometry, we would just find that the total plastic torque for total plastic capacity would just equal 4/3 times the total yield torque, which Ty would just be the triangular stress distribution that we had previously assumed here. So assuming a linear elastic region, and yeah, so the ratio between that rectangular torque and the triangular torque is just a matter of 4/3. Now when it comes to the torque twist relation, again, the angle of twist varies linearly as we're still within the linear elastic region. Once you break the linear elastic region, what we find is we get a parabolic function as a function of, technically it's a cubic function, where sigma y, phi y here would just be a constant because we would know what the angle of twist at yielding would be. That phi y is just the associated angle of twist for this case here. So we could calculate what phi y would be for that case there. And then phi would just be whatever the angle of twist is that you're considering. And so what we would find is an inverse cubic function that basically blows up to infinity as you reach closer and closer to the plastic torque. Which makes sense because, again, we're dealing with plasticity, so our deformations should obviously blow up. For torque, it's very simple. Once you start dealing with it for like beams, for example, it becomes a nightmare. All right. Anyone want to take a guess at what happens once the material yields and you unload it? Does anyone remember how it worked for axial loading? How did it work?
It would go back from wherever plastic yield, plastic strain point you went up to, and just go down the same rate of change as it would in the elastic range.
All right, and what happens if you loaded it again?
Wouldn't it?
And while still being linear elastically within that region? Would it still follow that slope?
Wouldn't it? Or wait, when you apply the load, let go of it, and then apply it again?
Yes. How would it behave?
I wanna say it would be the same as elastic.
It would behave linear elastically again until the yield stress.
Yeah.
Yeah, so you would basically get this, where if you were loading it and then you let go of loading, then obviously you get what's called residual deformation or residual stress development. But then if you started loading it again, it would follow this curve here up until the point of residual stress, and then it would just continue loading cubically, or inverse cubically. All right? And so these residual stresses, you get these really weird profiles where basically you would just have, for example, our base condition here for linear elasticity, and then you would have residual stresses that ultimately develop due to the permanent deformation, which would then, of course, be resisting any type of torque. And so then your stress development really just gets really confusing at that point, because then you have a summation of the two stresses. And yeah, so the gist of this is don't load your rods to yielding. All right, well, I don't feel like doing this example. Let me see, do I have to do this? I hate plasticity with rods. All right. Yeah, I think I'm gonna leave this. So I think I've tortured you guys enough today, and then I think next class we'll do the example. You know, especially since I want to make sure that I'm explaining everything right. So I'll say we'll actually end a few minutes early today. If you guys have questions, let me know. If you have questions about the homework that I uploaded today, let me know. If you guys need any help with anything relating to stuff that we have previously learned or have any additional questions, again, let me know. All right.